40. Okay. I'm thinking about the project. We usually do 3 people in a team, but we don't usually have that many students. So I'm thinking maybe of doing 4 in a team. I don't know. We'll see after this submission. If we still have 40, we'll consider that. So just to give you a little bit of orientation, today we're releasing a assignment about decision trees, which involves some programming. Not terrible, but those of you, if there are any of you who are kind of weak on programming, it's going to be require a little more programming, I think, than previous assignments. And that because we have a spring break coming up, it's going to be due in a long time. How much time?
In 3 weeks.
In 3 weeks. So you actually have 2 weeks, even if you are going to party all of spring break.
How long is the spring break?
I'm sorry?
How long is the spring break?
1 week.
1 week.
Yeah, usually spring break is 1 week. Yeah, I'm as clueless about spring break as you are, because I've never taken it.
Yeah, the fall break was very short, like it was 1 day.
Yeah, fall break is 1 day. Spring break is longer, because I think the spring semester is longer. I don't know why. But there's an American tradition of everybody descending on one miserable little town in Florida and drinking themselves to death. Those of you who went to American undergrad know what I'm talking about. So it's a great time to get research done. It's quiet. And so after that, there will be one more assignment about hidden Markov models, which is going to be the most challenging, I think, both because a combination of programming, but also getting it to work. But I think also the most useful assignment. I think it really helps you learn HMMs. And then after that, no more assignments, but I would expect you to start immediately. Maybe, in fact, you can start right now to form teams and work on the project. Well, you can't start working on the project because I didn't tell you what it is, because I haven't decided yet what it is. But we have open-ended. You can use whatever you learned in this course as well as whatever you learned elsewhere. And mildly competitive. Not competitive with regard to getting an A. I told you it's not hard to get an A in this course. But mildly competitive in that if you get the best results, you get chocolate truffles. And you get to be embarrassed in front of the entire LTI receiving them. So we have a tradition of at the LTI TG, at the end of semester party or whatever it's called, we announce the winners and give you the chocolate truffles. So that's the extent of the competition. And you get to write in your application to whatever thing you're going to apply next that you won the competition. That's fine. Okay, so we're back to decision trees. I said that there are, I think, 4 questions we're going to ask about decision trees. The first one was, what kind of questions to ask? It's a non-trivial question because the number of questions that is possible to ask is doubly exponential. To remind you, the number of possible binary questions about the history is 2 to the power of the number of different histories. And the number of different histories is itself exponential in the size of the vocabulary. So we cannot possibly even consider all the questions. We can consider a tiny, exponentially small fraction of all questions. So it's up to us to come up with a set of questions that we might want to ask. One particular category of questions is to ask questions about one particular position in the history. For example, about the last word of the history, or the next to last word in the history, or the word 7 positions back in the history. Remember that decision trees are not limited in their questions to the last few words, the way n-grams are. They could ask about the first word of the history. That is already a big restriction because you cannot express things like, was the word dog mentioned anywhere in the history? You could come up with a question like that, but it wouldn't fall into the category of questions that are asked about particular positions. You can only ask, is the last word dog? Is the word before it dog? These are all going to be different questions. Nonetheless, even if you restrict your attention to questions about particular positions, there are still way too many of them. How many different questions can there be about the last word in the history? I'm sorry? As many as there are words in the vocabulary. Yes? No? More?
But you could ask more kinds of questions than what's strictly in the vocabulary. You could be asking a question about its, say, for example, part of speech tag or
Right.
named entity category, and these are not strictly.
Right. So if you were restricting yourself to asking, is the last word a dog? Is the last word the? Is the last word of? Is the last word Brazil? Then there would be V such questions. But if you allow yourself to ask any question, any binary question about the last word, how many such questions would there be?
2 to the V.
2 to the V, and I really do expect you all to know that like this. So there are 2 to the V possible questions because there are V possible values to the last word, and each one of them could lead to the answer yes or no. So that would include asking about effectively every subset of the vocabulary. Does this word belong to this particular subset of the vocabulary? And how many subsets of the vocabulary are there? 2 to the V. So asking binary questions is the same as asking about a subset. And the set of all subsets is known as the power set. The power set of the vocabulary is of size 2 to the V.
So what does the empty set correspond to?
Empty set corresponds to a question that the answer to which is always no. It's not a meaningful question to ask. And it's not meaningful to ask the question the answer to which is always yes. So, okay, we're not going to consider 2 to the V, we're going to consider 2 to the V minus 2. But it's still a very large number. V is 100,000, 2 to the V is a huge number. And even if you take 2 away from it, it's still a huge number. Malcolm, you had a question?
Oh, so I was just going to ask that if you're asking questions about like part of speech tags or topic, like saying like is this word is the last word in a topic, could you just formulate it as saying is the last word in this set which corresponds to this topic?
Exactly.
Okay.
It's exactly right. Any question like is the last word in the determiner could be thought of does the last word belong to the subset of vocabulary which we define to be the determiner? It can get a little more complicated than that, because if you want to ask if the last word is a noun, well, whether the last word is a noun or not is not clear from knowing what that word is. If that word was saw, it depends on whether it was used as a noun or as a verb, right? So to ask about the true part of speech, we're asking about some latent property of the words. So that cannot be answered necessarily by just knowing the identity of the word. You could attempt to ask such questions, but we should restrict ourselves to questions that can be answered computationally. So instead of asking, is the last word a noun, we could ask, would the last word be classified as noun by Joe's tagger version 1.3? Right? A particular tagger, given the particular history, would it classify that word as a noun? That is a computational question. Whether this word is a noun is not necessarily a computational question. It's a question we have to answer, looking at it ourselves and deciding, and people could argue over it. So suppose for a moment we restrict ourselves to questions about individual positions. Let's say even the last word position, the last word in the history. There are 2 to the V such questions. That's a huge number. This comes to about 10 to the 100,000 divided by 3.2. 100,000 by about 30,000. It's 1 with 30,000 zeros after it. It's kind of a large number. It's asking about one word. How many elementary particles are there in the universe? We covered that already? I'm sorry?
Less than 10 to the 100.
Yeah, 10 to the 80 about. So there are 10 to the 80 elementary particles like quarks and stuff in the all known universe, all the galaxies and stuff. So this number is way outside our reach. So we can't even enumerate all these questions, not even a tiny fraction of them. Remember, each one of these questions corresponds to, is the last word a member of a particular subset of the vocabulary? So you can think about it in terms of, there are way too many subsets to consider. Which subset should we consider? So you can think about which subsets are useful. And you can use linguistics to suggest some subsets. Sets of nouns, proper nouns, plural nouns, singular nouns, closed form, closed function, closed sets, like function words, pronouns. You can make semantic classifications like the set of all names of days of the week. Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. That's a reasonable natural set. So you could include in your pool of candidate questions the question, is the last word one of the names of the week, of the days of the week, or one of the names of the months, or any other class that, is it a place name? And of course, some of these will be hard to answer for the same reason we mentioned about part of speech, because place names could also be, there's a place called Hope, Arkansas. Well, Hope is also an abstract noun. So you'll need to run a word sense disambiguator to answer that question. But you can nonetheless define a set of all words that could be place names or that could be abstract nouns, right? And that's still a meaningful question to ask. So we can come up with large sets of questions easily. We can come up with sets of tens of questions, of hundreds or even thousands or tens of thousands of questions. It's still going to be a tiny fraction of all possible questions. You can even think of computational ways of deriving useful classes of questions, but it would necessarily have to be a greedy algorithm. So imagine the entire vocabulary, and you're trying to come up with a meaningful partition of it. And remember, there are 2 to the 100,000 possible partitions of it. And you can come up with a heuristic of what's a good partition. A good partition is something that has high mutual information with something else. So for any partition that you're evaluating, you can calculate its mutual information on the corpus, maybe with the next word. But you cannot evaluate all 2 to the 100,000 of them. So you can start with maybe one random one and take each member of this set and consider moving it to this set and ask whether it increased the mutual information or reduced it. You can afford to go over all the members of this set and even all the members of this set and to ask about moving them this way or that way. So you can afford to check all possible one moves of changing the size of the subset, right? Because there are only 100,000 of them. 100,000 is a cheap number. But you cannot afford to consider all possible moves of large chunks. So you can consider all moves and move all the ones that result in an increase in mutual information or whatever other measure you're looking at, and then iterate again. After that move, try again to move one. That's a heuristic, and that's a greedy method. It will not give you an optimal result, but it will give you a decent result. So there could be a lot of work that goes into just selecting the set of questions to let the decision tree ask. Okay? Suppose somebody did work for us, and by the way, most of this work is linguistic, not statistical. It's using your notion of what language is to decide what questions are meaningful. Although what I showed here is an attempt to inject some statistics into it in the sense of basing that decision somewhat on data. But for the most part, we will not do this, and we will just come up with a set. Step 1, come up with set of questions. And I would say maybe between 10 to the 3 and 10 to the 10 questions. Anything that your algorithm could handle. It depends on what you're going to do with it. But, you know, big machines these days can handle this much. But it could be 10 to the 30,000. And this is mostly linguistic work. Here is where you want to involve linguists and your own linguistic intuition. The second question is, okay, now you have a set of questions which can be thought of in the standard CART formalism as attributes. Or normally, you're given in a CART framework, you're given attributes and you can ask questions about any one of them. But here we go directly to the questions. These are the questions you can choose. Now build the tree. So the question is, decide recursively on the next question to ask. From that pool. From the pool. This pool. So what do I mean by recursively? I'm assuming that you've all seen how CART works. You start with the root, and you place a question here. Question about the history. And the question has a yes answer and a no answer. And you assume in the beginning that all the tree does for you is it splits all of the, splits any incoming history into going to here and to here. And now you're supposed to give a distribution here. Probability of any word in the vocabulary being the next word given that the history, let's say we call this question question 1. Given that the history, when fed into question 1, gave a yes, and here we'll have a distribution over words under the condition that the history fed into question 1 gave a no. Before you ask the question, or before you know the answer to the question, there's a certain unconditional distribution. P of W. This is the unigram, right? It's a distribution over all the words without knowing anything about the history. That distribution has some entropy. We all know how to calculate that entropy. If we're given a unigram, we know how to calculate its entropy. It's a sum of P log 1 over P. Each one of these guys have its own entropy. The entropies here are H of W condition on Q1 of H being yes, and here it's H of W condition on Q1 of H being no. We can calculate the average conditional entropy by combining these two with weights. The weights are going to be proportional to how often question 1 is answered yes and how often it's answered no. Right? And then we can look at the reduction in entropy by taking the original entropy before asking the question and subtracting from it the average of these. So here's where information theory comes into play. And all of that is equivalent to effectively calculating the mutual information. Calculate mutual information between the thing we're trying to predict, W, and the answer of the question on the history. Right? We know that the mutual information is defined as what the entropy was before we asked the question and what the entropy is on average after knowing the answer to the question. So we're going to use the mutual information as our measure of goodness of the question. So I'm going to choose question 1 as the one that maximizes. So I'll give this pool a name, pool of questions. I'll just call it questions. Now, I don't want you to think this is a subscript of something. What do we want to call the pool of questions? I can't call it P. Call it pool. Come up with pool of questions. Now,
Small Q for a question and big Q for the pool.
I'm sorry?
You can use small Q for a single question and big Q for the pool.
You know what? You're right. Maybe I should. But then everybody's going to curse me for changing these. And OK, Q is a question. Next year. Q is a question. And pool is pool. OK? So now I'm going to choose Q1. I'm going to put here the question that minimizes the average entropy of the leaves. How much computation is involved here? A lot, but it's doable. The size of the pool is something that I can kind of afford to loop over. And this calculation inside each iteration of the loop is non-trivial. You have to calculate these things, right? You have to calculate the probability of each word, and you're already going to estimate it. It's all going to be estimates from the training data. This, in fact, is an estimate too, and therefore this is an estimate. But we're kind of ignoring that fact. So these are estimates, and this is an estimate, and therefore this is going to be an estimate. So maybe I couldn't do 10 to the 10, but maybe I could do 10 to the 6 or 7. It all depends on what kind of model you're going to use. If you're going to use an n-gram, then for each question, you have to train a new n-gram here and here. Right? This is an n-gram for all words, for all training data where the... Remember, you can think of the training corpus as a set of pairs of H and W. You can take a long training corpus, W1, W2, W3, starting with beginning of sentence, and put a window over it and generate pairs of history, word, history, word, history, word. The history grows and the word comes after it, and then if you decide the history only extends to the end of a sentence, then every time you reach a sentence boundary, the history starts again. But in principle, training corpus can be viewed as a set of ordered pairs. But the first member of the set of the pair is history, and the second member is word. And you can think about it as a mapping from a history to a distribution over words. So you have to decide what kind of model you're going to plug in here. But an n-gram is a reasonable choice, maybe even a bigram, maybe even a unigram. You can do it based on the unigram. So let's stick to the simplest case, because we know we're not going to stop here. We're going to look further. We're going to further expand with more questions. So let's assume that we're going to build a unigram here. So I'll put it here. Because all we care about, all we can rely on at this point is only what the question answered us. So that makes it much faster, but it's still only an estimate. Furthermore, I don't know if you remember when you learned about decision trees in general, the rule, which may have not been presented with this terminology, they may have used something called information gain, but information gain is the same as mutual information. The rule is a heuristic rule, and it's a greedy rule. It does not guarantee that it will give you the smallest possible tree at the end. The same is true here. You're not guaranteed to get the best tree or the smallest tree, or you're not guaranteed to get anything. But it's a reasonable heuristic. So we're going to use this heuristic, and then we're going to go to each one of the children and ask this question recursively. Now I'm going to ask, what question do I put here? And again, I'm going to, let's call it Q2. I'm going to answer it the same way. It's whichever one that maximizes among all the set of questions in the pool that have not been asked yet, of course. I'm not going to reconsider Q1. That maximizes the mutual information, or the estimated mutual information, between what and what? Between the next word, the question, conditioned on Q1 of H being yes. So subject to all the histories and the training data for which Q1 answered yes and therefore went this way, now I'm going to ask about another question, make another split, and I want to know which question to ask that would have the most information about W. Yes.
In this framework, is it important whether you go depth first, choosing your questions, or breadth first?
It's only important in the sense of when you decide to stop. Because the decisions don't affect each other, right? So how far down I go here will not affect what happens here once I come here.
Maybe question 3, if you go down here, is actually a better fit if you put it on the right.
But this algorithm, as I described it, does not know how to backtrack.
Okay. So
And if it is a better fit here, I will come across it here. So when I say that I will not consider question 1, so let me make the general pool here. I'm going to consider all the questions in the pool except those that are up my path, except those questions already asked up my path. It has nothing to do with whether it gets asked here. It doesn't make sense to ask a question that was asked along my path because it was already answered. It will obviously not provide any new information. So I'm going to consider everything except what's up my path. And in general, the conditioning here would be not only about Q1, but about every question that was asked up my path. So it's the same. So in the general case, let's say I have Q5 here. Q5 would be maximizing over all the questions in the pool except, of course, Q2 and Q1, and conditioned on Q1 being 0 and Q2 of H being no, because this is a no and this is a yes. So I will build a tree recursively. The order does not matter for the answers I get, because I only consider what's happening up the path. Yes?
Is this different from that ID3 algorithm? Because I think in ID3 algorithm, the next question will be chosen from only the pool.
This is the ID3 algorithm. There's no difference. The only slight difference is that my goal, my goal is in the leaves to produce a distribution rather than a single category. Because my goal is that for the tree to represent a conditional distribution, not a particular category. So it's a generalization of ID3, but the algorithm itself works exactly the same.
Yeah, but I mean in ID3 algorithm, the next question to be asked will be chosen from the pool, excluding those has been asked whenever in the tree.
No.
No, it's only up the path.
Only up the path. Specifically, you could build a tree that asks about x5 here, and x7 here, and x7 here. That could happen in ID3 without a problem. In fact, it's even likely to happen. If there are two variables, x5 and x7, are very informative together, they're very informative, then it may very well choose that. Yes?
So we have this like for one word and one history. Like we start asking the question according to the history of this word, and then we go yes or no, and then again, I mean the H.
So H is not one particular history. It's used here as a variable, as a random variable that holds holds different histories. So let me try to make it more explicit. The training corpus consists of H1, W1, H2, W2, HN, WN. For example, if the story was there was a king that's the first sentence in my corpus, then H1, W1 would be, beginning sentence would be my first history, and there would be my word, right? This is history 1, this is W1. History 2 would be beginning sentence followed by the word there, and then the word was. Was is W2, and this is H2. H3 would be beginning of sentence symbol, there was, and W3 is A. Okay, this part is clear, right? So now let's only focus on this abstraction, that we have a set of pairs. Now, what is the entropy? What is the distribution estimate P of W? That's just a unigram. We're ignoring the histories, and we're just, let's say it's, I use maximum likelihood. It's just the count of the word divided by this n. This n. What about, what's the entropy of this? Entropy of P of W is sum of pi log of 1 over pi. And I need to be a little careful. If something occurred 0 times, I need to smooth it somehow. But basically, I can calculate what the entropy is. And that's unconditional entropy. That's the entropy of the unigram when I don't consider the history at all. Now let's compare it to the case where I consider history. P of word given Q1 of H equals yes. I basically apply the question to all the histories and split them into two sets. Those where the history gave the answer yes to question 1, and when those will give the answer no. And I'm now going to base this only on the words that came with the history, the words that came with the histories that said yes. And separately, so I basically split my training data into two different training sets based on the answer to question 1. And I build a separate unigram here and a separate unigram here. Okay? And these unigrams have their own entropy. And the average of these entropies, subtracted from the original entropy, gives us the mutual information. Does that answer your question?
Yes. Like 2 questions here. Like first, like we are asking binary questions. So would that be the, for example, the next word in the history is, say, there, and another word in the history is not there, right? So it's like one extension versus every other possible extension. Or would we like bucket words, for example, like a set, some does the next word belong to some smaller subset?
All of the above. So that belongs in step 1. You can include there in the pool of questions, you can include questions about particular places, particular positions in the history, like questions about the last word of the history. And even there you can include specific subsets of the vocabulary. Or you can ask, does the word dog occur anywhere in the history? You can even ask, does the word dog occur in the last 5 positions of the history? Or is a mammal mentioned anywhere in the last 7 positions of the history? You can ask any question you want. The question is, what would be a reasonable number and a reasonable choice of questions to include? Any question that can computationally be answered, given the history, can answer yes or no, is valid to include.
Okay, actually, then I have a third question. The second question would be, okay, we're like considering progressive inclusive histories. So does it actually mean that we simply unable to make the same question twice? Because we're always dealing with inherently different questions. They kind of considering a longer and longer n-gram. So we cannot ask questions about n-gram length.
It's true in general that in a tree, you don't find a question somewhere that occurred further up along the same path on the tree. Because since that question was already answered when you got here, it will be answered in exactly the same way with all the data that goes there.
Right, but I'm talking about that, I'm asking whether it is like physically impossible. Because we are like kind of extending a history, right? So we cannot ask, because the first question, for example, is the n-gram is W1, some word W1. And then the next question would be whether the history is W1, W2, some words W2, but we cannot ask about the word W1 or...
If you fully figured out W1, but remember that these are binary questions, so you might not fully figure out the meaning, the identity of W1. You could figure out if it's a noun or not, or if it's a mammal or not, but you may not have figured out exactly what it is. So this brings up a good point. When you ask questions about the identity of individual words, you are finding out something about these words. Maybe one bit of information, maybe less than one bit. You can think of figuring out the identity of a particular word incrementally, one bit at a time. So if the last word if this is the entire vocabulary, and the last word is this word, this is the entire vocabulary, you can ask a question that divides this in two, and in that case the answer would be yes for this word because it's on this side. And then you can take this and ask further down the tree, you can ask another question, split it this way, and then you can split it this way and split it that way and so forth, until you can eventually, if you want, zero in on one particular word. You will do that by a long set of questions that would be at least, on average, log size of the vocabulary, number of questions, right? And that is effectively what an n-gram does. An n-gram starts by figuring out the identity of the last word of the history, completely figuring it out, conditioning on the fact that that word is that particular word, and then conditioned on that, it goes and looks at the identity of the word before that, and then the word before that, and so forth. At some point it stops. What the decision tree allows you to do is to ask these questions partially. You don't really care what the exact word is. It's good enough for you to know that it's a noun, or it's good enough for you to know that it's a mammal. So a decision tree has more expressive power. It can decide on a stronger or less strong partitioning of the data. In fact, this is a very useful way to think about what decision trees and n-grams do. They fall into a large class of models known as partition-based models. These are models of conditional distributions that partition the space of histories, partition the part that we're conditioning on, in any way you want. It's up to you to decide how to partition it. So a decision tree can implement any partition. There I drew the vocabulary because I was referring to questions about a specific word. But now imagine that you can ask questions about any history. So this is a space of all possible histories. Obviously a very large set, a very large space, histories. Now in this space, any question corresponds to a particular partitioning, where this side is yes, this side is no. Right? Every question about histories, every binary question corresponds to partitioning, and vice versa. Every partitioning corresponds to a particular question. We're only considering a few million questions, and there are many, many more, but nonetheless, that's what we can do. So a particular decision tree corresponds to first impose this distinction, that's at the root, so that would be Q1. And then, if you fell on the negative side, impose, let's say if you fell on the positive side, impose Q2. This would be yes, this would be no. And if you fell on the negative side, call it Q3. This would be say yes, this would be no. And that would correspond to a tree that looks like Q1, Q2, Q3. Q2 is on the yes side. And let's say we split Q2 this way with a yes and a no, and this would be Q4. We split it on the n side, so that's yes, no, so this is Q4. So any tree corresponds to this kind of a view. And you can make these partitions as detailed as you want, and you can stop at any point and look at this as an equivalence class of histories. Every cell here, like this cell, corresponds to a particular leaf and corresponds to the set of all histories that provide the same answers along that path. Right? There are incredibly large number of histories here. We did not of questions here that we of histories here that we did not consider, but we know they all share the property that they all answered all these questions along the path exactly the same way. And then we can build a little unigram here. And we can build a little unigram in each one of these. So each one of these cells will have its own unigram. And hopefully these unigrams are going to be more sharp, more peaked than the original unigram that is not conditional on anything. And therefore its entropy is going to be lower. So ideally we want to ask questions that lead to cells that are as far from uniform as possible, that are more peaked, that tend to provide the same answer. This is a generalization of a typical decision tree. In a typical decision tree, at the end, you just provide a single number or a single category as an answer. Here, we're not going to try even to provide a single category because we don't believe that the underlying function is deterministic. Even for the very specific history, very long history, you can ask any questions you want about it. Even if you identified one particular history, still more than one word can come after it. It's a stochastic process. So we're not going to give one word as an answer. We're going to give a whole distribution as an answer. But we're hoping that this distribution would be very peaked. Yes.
So I had a question about how we form the decision trees. Suppose the last word is king. The first question can be about the second word, and the second question can be about first and the second word.
Absolutely. Any of those. Now, if you were to construct that tree on your own without using mutual information, you just try to do it based on linguistic concepts, it might make sense for you heuristically to start asking about the last word and to ask more and more questions about the last word until you figure it out to a great extent. Maybe you don't know exactly what the word is, but you know if it's what part of speech it is, and you know what semantic class it is, and you know lots of groups. And then you might decide, enough about this word, now let me find out about the word before it. So it might make sense for you to ask questions, start with the last word, and the word before that, and the word before that. But you don't have to. You might even consider questions that are more distributed, like, is any military term mentioned in the history anywhere? So you're trying to figure out the topic, right? You're free to do that. When these trees are built automatically, they do tend to ask, you can see that effect, that most of the first questions are about the last word, and then they start creeping up with questions about the next to last and so forth.
When you're calculating the mutual information for progressively lower nodes in your tree, you're starting to condition on a longer set of questions. Do you at any point limit the number of questions you look back in the tree, or you just take the whole path right up to the node?
I don't look at the path along the node. I look at all the questions in the pool. I just exclude the questions that were in the path.
For example, you say Q5 is equal to...
I maximize here over the pool, except I don't ask questions that were already asked.
Right, but it's conditioned on Q1.
Ah, okay. So the conditioning.
How do you condition right up to
Yes, absolutely, because you will be in that situation when you are, both when you use the tree, you will know what the answer was to each one of these questions.
Your estimates for the probabilities of this conditioning, are those going to get progressively worse?
Yes, good point. I start with a 100 million word corpus. So I have 100 million pairs of history word. So my unigram is pretty good and my estimate of its perplexity is also, of its entropy is also very good. Now I came up with a question. It split the data, let's say, more or less equally. I came up with another question for each node, for each child. I keep doing that. After 10 questions, I have more than 1,000 children. Even if the data is distributed among them uniformly, which it may not be, even if it's distributed more or less uniformly, each one of these 1,000 leaves now has only 1,000th of the data on average, right? So now I started with 100 million words, now I have only 100,000 words. If I keep doing that, as I go further and further down the tree, I will be basing my conditional unigrams on less and less data. So they will not be as good estimates because now my variance increases. My bias decreases because I'm considering more context, but my variance increases. And my estimate of the mutual information is also going to be more wobbly. So I will need to stop at some point. If I did not take that into account, I could always do a better job by splitting it more and more and more and more, and I'll grow a monstrous tree. But the estimate in each one of the leaves is going to be very unreliable. So I'm going to stop after a while. That was going to be my question number 3. When do we stop?
So in general, as you ask more specific questions, your bias decreases, but your variance increases?
That is correct. Asking more specific questions is like choosing a higher order n-gram. Right? You're conditioning on more and more and more of the history, and therefore you're making the context more and more similar to the one you're considering, but you're basing it on far less training data, and therefore your variance grows. There's really not much difference between decision trees and n-grams. N-grams are the degenerate type of decision tree where you're only allowing yourself to ask about one word at a time. You're only allowing yourself to ask in reverse order of the words, starting from the last word, the one before that. So the order is fixed, and you're only allowing yourself to ask in chunks of asking the entire identity of the word. You're not allowing yourself to keep it as a class of words or a category of words like mammals. So decision tree is a generalization of n-grams that allows you to ask any question in any order to any degree, including questions that combine information from many words in the history. So I would say that decision trees are, or trees are the ultimate partition-based model, not in the sense that they're necessarily the best, but in the sense that they're the most expressive. They're a superset of any other partition-based model. They can represent any partitioning of the history. Leon.
Is n-gram a binary decision tree?
It can be implemented by a binary decision tree.
But then you won't be able to make a decision for the whole, for a single, next step. It won't be a single step on the.
Right. It won't be a single step. But any n-gram can be implemented as a decision tree.
But is there any value to consider non-binary decision trees?
Possibly, not a theoretical one, because any non-binary question can be represented as a set of binary questions. But so it would not increase the expressive power of the family of models. But you might argue increasing the expressive power is not necessarily better. If you can introduce a smaller set of models to consider, but you can argue that's a better fit, that's better, right? That goes to the question of bias. You want to introduce bias is not bad. Bias is good as long as it's the right bias.
Right, but would it be faster to train because instead of making...
Possibly, yeah. Well, certainly n-grams are faster to train than a general decision tree. General decision trees are not easy to train. They're computationally very expensive to train. In fact, you have to introduce shortcuts in many, many steps.
And there's also the power of increased size of question pool. So we know that there are some good questions that are not binary, like what is the last word? It is no. There can be B answers, But if you consider non-binary questions, then your the size of the question pool is no longer 2 to the b, but you know it can be a much larger number than 2 to the b power.
Right, but you anyway, you are at still like 2 to the power with still a ginormous number. You artificially like choose only the questions that you want to ask, so it might not be bad.
Right, right. So there are lots of good reasons to consider other types of questions in the tree, not necessarily binary. But what I want to point out is that from a theoretical point of view of what things can be represented and what things cannot be represented, binary decision trees can represent any partition-based model. Yes?
So also my earlier question about like the longer your branch of decision tree, the more variance you have. Does that generalize to the more complex model you have, the more variance it'll have and the less, or the more variance and less bias?
In general, the more parameters you have, the less bias and the more variance, certainly. So one other way people refer to it is to say you have a lot of parameters, you have a fixed amount of data, your estimates are not going to be so good. A more accurate way of saying it is that the variance of the estimate is going to be large.
So you need to have more data in order to like get over your parameters.
Right, right. Okay, so we have a recursive definition. I mean, I can rewrite it in a generic way if you think it's useful, the way each question is chosen. But I think I described it verbally enough that you look up the path, you condition on the questions up the path, and then you consider all the other questions to see which one gives you the most information about the identity of the next word. And it's all an estimate based on the data. So now you have to decide when to stop growing the tree. And the reason to stop is the reason that was mentioned here, is that your estimates are going to be based on smaller and smaller amounts of data. You can see it here. If you got to a very small space here, there may be very little training data that falls into this space, and therefore your estimate of the unigram from that training data may be unreliable. So you can come up with a variety of heuristics to decide when to stop growing. And it's not a single decision. It's a decision that applies at every branch of the tree. Every leaf, you have to decide whether to split it further or not. You can do it based on some absolute number of training examples that fall into it. Once you go below 10,000, you stop. You can do it based on how much mutual information you expect the next split to give you. So if I introduce another question here, which would be the best one? And now that I know which is the best one, how much does it actually give me? And I don't believe that it really gives me this amount because it's an estimate, and it's an estimate based on a very small amount of data. So if it's a large number, maybe I'll do it. But if it's a small number, maybe it's time to stop. So these are all heuristics. The most commonly used heuristic is to keep some held out data that is not used to choose the best question. But after you chose the best question, you go and try it on your held out data, and you see whether it actually reduced entropy there. And if it didn't, it's time to stop. The problem is that you need the amount of held out data that you need is quite large. In fact, it's roughly as large as the amount of training data, because the only data there that you could use to make that decision is the data that fell along the exact same path. Okay, so we answer the question, how do you come up with a pool of questions? The answer is via linguistics and your intuition and your knowledge of the domain. We answer, one answer to the question, how do you recursively build the tree, is by maximizing mutual information with the next possible question. The question of how do you decide when to stop growing the tree is answered with some arbitrary heuristic or by keeping held out data and seeing the effect on the held out data. You don't have to stop growing the tree at exactly the same depth everywhere. You can grow an unbalanced tree, that's fine. And then the last question we need to ask is, once we fix the tree, once we learn the tree, what's the best estimate or model that we can base on it? So imagine that you have a tree here. Now you have 1, 2, 3, 4, 5, no, 5 leaves. You took the training data and you poured it down the root and you let it propagate down. So now you have some bunch of training data here, bunch of training data here, bunch here, and bunch here. You're only considering the words in the training data. So it's an array of words. I'm sorry, not here. 1, 2, 3, 4, 5. This is a question. So you build 5 unigrams, and now you can, given a new test example, given in the form of a history, a new history, you check to see where it falls, and if it falls here, you provide this unigram. If it falls here, you provide this unigram, and so forth. So that's a very simple answer. You just provide the unigram that's at the bottom at the right place, corresponding to the history you're looking at. But, as you guys pointed out, these estimates tend to be based on relatively small amounts of data, and they may have a high variance. One solution is to not grow the tree too much so that they don't have a high variance. But here's another solution. Instead of relying on the estimates from here, smooth your way up the tree. Suppose that your new history fell into here. New history. You create one unigram based on the data that's here, but you create another unigram based on the data that's here before it was split in two. So it includes both the data from here and the data from here. Arguably, the training data that fell here is quite relevant to what happened here. Maybe not as relevant, maybe the data from here is not as relevant to this as the data from here itself, but it's more relevant than the data from here. So there's some relevance, and there's certainly more data here. And you can apply the same argument to go up and say the data here is more relevant for what's going on here than the data that went this way. So you build a unigram here as well, and you build a big unigram here. So now you have a path of unigrams, 4 in this case, but in the real world it'll be maybe thousands or hundreds. And they form a hierarchy of models that trade off what? Bias and variance. At the bottom, you have the least bias, but the most variance. At the top, no conditioning, you have the least variance, but the most bias. So this is a form of shrinkage. You can shrink this path together. So it would be the probability of word given your new history would be a sum lambda j pj of w given the history. And the pj are going to follow the path. Follow path from leaf to root. So now we can, after we froze the tree, we could build a unigram not only for each leaf, but for every internal node as well. That's not much more work. The number of internal nodes is comparable to the number of leaves, right? It's the same number. So you just doubled the number of unigrams that you built. So we build those, and we fix them. So if you have 10,000 nodes, or 10,000 leaves, you have 20,000 nodes together, leaves and non-leaves. You build 20,000 unigrams. And then for any new history, you find a path, and you interpolate the few. In a tree of 20,000 nodes, the depth is only log of 20,000, which is not too bad.
How do you estimate the lambda?
Thank you. Is that your question too? Yeah. That's the remaining question. How do we estimate the lambdas? Any suggestions?
Holdout set?
I'm sorry?
Holdout set?
Held out set, yes. So held out set is good. But now let's estimate how many weights we need to estimate. How many weights will you need to estimate? So let's say that there are a total of n nodes. So what's the depth of the tree on average? Log n. Depth, average depth is log n. How many weights do you need for each type of history? A particular history new got here, how many weights would we need? We need log n weights, right? So a number of lambdas overall would be log n. That's how many are combined here up the path. And how many paths are there?
N. No.
Half n or n. I mean, depends of if n is the total number of nodes, half of them are leaves, right? So n over 2, let's say. That's doable, but it's a lot. If you have a tree of 20,000 nodes, n over 2 is 10,000. Log of n is what? Log of 1,000 is 10. 3, 13. So we're at 14 point something. Log of 20,000. So 14 times 10,000. That's a lot of parameters. You will need a very large held out set. There's a way we can economize on parameters. The way we can economize on parameters is, right now, what we're doing is for every leaf, we're computing a completely new set of ways of combining. But you could argue that for this leaf, you're combining, here's weight number 1, number 2, number 3, number 4, and this is number 1, number 2, number 3, number 5. So maybe we should first create 1, 2, and 3, some optimal combination of those, and then just modify these. It's not something out of nothing. We are giving up something. We're creating, it's a more constrained model in that we're forcing the ratios of these to be the same regardless of what comes here. But it will result in far fewer weights. So let's see how we do that. What we do is we start from the top rather than from the bottom. We go to the first child and we create a linear combination of just these two models. There's only one parameter. We estimate it from held out data, and we store this parameter here. So this parameter tells us how much weight to assign this model when combined with its parent. Then we do the same thing here. Then we recursively go to this child and say, given that this one is smoothed already in a fixed way with this one, consider it a single model, single smooth model. And now come up with just one weight for this one to combine with this one. And then come up with one weight here to combine with this one. So at any point, we come up, for every node, we have to come up with just a single weight, which is the way to combine it with the already smooth model sitting at its parent. And therefore, the overall number of weights we need is the number of nodes in the tree. So we cut out the log n part. Okay, so we have only the n part. Maybe there's a factor of 2 there, but log n is still can be quite large. So it's order n as opposed to order n log n. Yes?
Can you say again what's that n over 2?
Oh, it depends on how you define the number of nodes. If you include the leaves and the internal nodes, if you only count the number of leaves, let's say there are n leaves, then you ask how many non-terminal, non-leaves nodes do you have? And the answer is another n, roughly, right? As a result, the overall number of nodes is 2n. So you could say that this is n, but the overall number of nodes is 2n. It's just a counting thing. Yes?
In the smoothing thing, you say you start at the root and you interpolate it only with its left child.
No, you interpolate Every child with its parent.
Every child with its parent.
Right.
Then
With its smooth parent.
yeah, but then you get one set of weights for the left child and one set of weights for the right child, right?
Right.
But then that's not n weights anymore.
Well, it is, because you only are choosing one weight for each child.
For each child, but when that child becomes a parent, it has two weights.
No. Let me do it. Okay. Here's a parent, child, 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 and more children. Each node has associated with it a unsmooth unigram. So let's call it unigram unsmooth. Let's say smooth as a wiggly. Okay? This has a unigram. This is a unigram. They all have unigrams inside them that are unsmooth, that are based on just the relative frequencies. Okay? Now I go to this child and I say, what weight do you want to give this guy so that it has optimal combination with its parent? I give it some weight lambda. That implies that the parent gets 1 minus lambda. Once I give it lambda, the combination of the parent and the child together, this would have 1 minus lambda, now forms a smooth model. And I take the smooth model and I put it back here. Now when I go to its child, I ask it, what weight do you want to combine yourself with that smooth model?
Get it?
So I only store 1 lambda in each node. I don't store anything at the root. Okay, so we answered all the questions. These questions did not originally come up historically in the development of decision trees. If you look at the decision tree book, the famous CART book that came up in '84, it didn't consider density estimations. It considered regression and classification, and it usually assumed that the questions are going to be evident in the representation. You had n attributes, so n inputs, and you could ask a question about each one of them. So it didn't deal with the question of which questions to ask. It did deal with the question of how to derive the tree, pretty much using this mechanism of mutual information, even though it may not have used this terminology. And it dealt with the question of when to stop growing the tree. It tried all sorts of heuristics and ways of doing that. It didn't deal with the fourth question of smoothing. Maybe a little bit, but it wasn't as necessary, because when you deal with language and with estimating multinomials, you're in a much more sparse situation than you usually are. So once these 4 questions had some proposed answers, a bunch of people at IBM decided to try it. The year is mid to late 80s. Yeah, mid to late 80s. By the time it was published, I think it was 89. The paper is, by the way, linked from the course website. It was the first time decision trees were applied to language. I happened to be there. I was lucky to be there right around the time they were doing that, maybe a little bit later. I was there in the summer of 80. No, I was there, I'm sorry, in the summer of 92. They've already finished doing that, but I heard the stories. They had a farm of computers that was working on this day and night for months. Because one nice thing about the algorithm for doing this is it's highly parallelizable. You can work, once you split the tree, and you're thinking of splitting this one, the decision to split this one does not depend on the decision how to split this one. So you can literally farm off individual nodes to individual computers and let them work on the best way to split it. So they had, dozens of computers working for months at a time to combine a tree and smooth it and use it. And they had great hopes for it. They thought it's going to beat the heck out of n-grams because, as I argued for you, n-grams are a special case of trees. right? So the space of all decision trees is bigger than the space of all n-grams, and surely there are some models in there that are not n-grams and are better than n-grams. The results were quite disappointing. They did manage to improve somewhat on n-grams, but only by a few percents. You'll see in the paper how much that is. So they were majorly disappointed. They try to salvage some of it by asking the following question. Say, okay, suppose perplexity is not much reduced. That means the average log probability is not much reduced. But maybe we're good at reducing big surprises. We're not so good at reducing the average surprise. We reduced it by a little bit. But maybe we're good at reducing big surprises. Why is that important? Because when you combine a language model with a particular language technology like speech recognition, the places where you make mistakes, like recognition errors, tend to be associated with big surprises in the language model. Right? When the language model, it doesn't have to be, and it's not the only way of making a mistake, but it's a very common reason for the speech recognizer to give you the wrong answer is because it really did not anticipate that word. It really thought the probability of that word is very, very small, wrongly. So they actually showed empirically that if you count, if you look at all the places where the speech recognizer makes a mistake and you look at the log probability of that the language model gave the correct word there, you will find that often it happened when the language model gave it a very low log probability, a very low probability, therefore was very surprised. So they went and counted the fraction of the times on the same test data that the n-gram was surprised. I think their cutoff was 10 to the negative 4. So any probability of less than 10 to the negative 4 was considered a big surprise. And they showed that the decision tree was less prone to big surprises. It had a smaller fraction of big surprises. That's the most they could say in that paper. Another thing they kind of managed to do is, maybe for fun or maybe for insight, they asked themselves, well, how does the decision tree see language? What does it think about language? Well, one way to answer the question, how does a model see language, is to ask the model to generate language. Did you ever see language generated by an n-gram? I'll bring it to class next time. It's a lot of fun. When a unigram generates language, or pseudo-language, it looks funny. When a bigram generates, it looks different, funny, a different kind of funny. When a trigram, when a high-order n-gram generates language, it looks very good for a while, and then it looks funny. You'll see what I mean when I show it to you. But I want to show you what it looks like when a decision tree generates a language. Sorry, I did not scan it, so I'm going to use old technology. Where are my lights? Oh, here they are. So their decision tree was trained on several tens of millions, maybe even 100 million words worth of romance novels. It's like Harlequin novels. Do you guys know what these are? These are really cheesy, novels, lots of dialogue and stuff. So I don't know if you can see that. I'll try to zoom in.
It's really surreal.
It's surreal, but it looks like it could be a Harlequin novel, right? The nice thing about it is it looks very grammatical, right? You will not get that with an n-gram. In an n-gram, you'll get the beginning of a quote, and then once you move past the scope of the n-gram, it will forget to close the quote, right? But here, it doesn't forget to close the quote. That's a result of the questions on the history being able to go very far into the history and ask, is there an open quote somewhere? So I can put a close quote. Yes.
Did they argue that the decision tree could learn language in a more structured format?
In a more structured format?
Than an n-gram model?
They claim that decision trees can learn stuff, regularities that n-grams cannot learn, and I agree with that claim. They didn't manage to do it here much, but the claim, I think, is still true. I think the big claim here is at the bottom. Right. But I think it's, other than being funny, I think it's really instructive to see what comes out of models. And I hope I remember to bring you next time examples of different n-grams. So we're not quite done talking about decision trees. We've done enough for you to do your assignment. But we'll talk about it a little more next time. After they failed here, they kind of went home with their tail between their legs and felt very demoralized. But a couple of years later, they said, we think we know why it went wrong, and they tried again. And I'll tell you about that next time. Yeah?
Quick question. You see the phrase, like, you know.
Uh-huh.
So are they capturing long, like phrases being repeated? Or?
I think that's captured by standard bigram information. Yeah, I think so.
How many questions did they have in their pool for?
I don't remember the number. I strongly encourage you to read the paper. It's not a very long paper, and it goes into a lot more detail than I did in class. It deals explicitly with the question of what pool of questions to ask. And they introduce something they call the pylon, which is an elaborate question with lots of sub-questions, but at the end it's all get mapped into a yes or a no. So they allow that kind of a question. How many? I'm guessing at least in the millions, maybe more. Another question is how big this tree is. As far as I remember, it was in the tens of thousands of nodes.
And so it would have depended on their headouts as well, wouldn't it? Because to rely on your lambdas, you have to have.
They didn't have lambdas.
They didn't smooth it?
They did smooth it, yeah. I think that method I described, I think, came from them.
Yes. So
Yeah.
So to estimate like maybe a million, thousands of lambdas or maybe a millions of lambdas, you need a huge set.
Right.
So
Right. They worked with the hundreds of millions of words of training corpus, and like 300 million training corpus. I don't remember exactly, it's in the paper. At the time, it was considered really huge. Today, it's no big deal, but at the time, it was, I think, the largest corpus assembled. Yeah. The held out data is used in two places. One is to decide when to stop growing a tree, and the second one is to smooth the lambdas. All right, thank you.